Okay, let's unpack this. Today, we're doing a deep dive into an engineering concept that is, it's really at the intersection of just high tragedy, incredible technology, and,
Yeah,
well, absolute
it
physics.
is. And it sounds, I mean, let's be honest, it sounds ridiculous at first glance.
It sounds like something out of a cartoon safety invention.
Right.
But the seriousness of it and the motivation, you just can't overstate it.
It's the ultimate what if in aviation safety. The sources you shared with us, they cover everything from, detailed crash data, historical NASA experiments, all the way to this proposal for Project Rebirth.
Right, the AI-powered external airbag system.
And it was a finalist for the James Dyson Award, which tells you something.
It does. So that's our mission today. We're going to distill the core mechanics of this really audacious proposal. We'll compare it against historical crash safety, and maybe most importantly, we're going to wade through the really deep and often kind of brutal technical skepticism it's faced.
Yeah, from all over the aviation world.
We need to figure out, was this a brilliant, impossible dream, or was it a realistic, a Hail Mary for a crisis?
It's a really compelling story. I mean, the ambition of the students who came up with this is just enormous. They were driven by this desire to solve a problem that, frankly, current engineering just hasn't cracked.
But physics and economics.
They are very harsh gatekeepers,
Mm.
especially in the aerospace industry.
And that profound motivation, that emotional root of Project Rebirth, that's really where we have to begin, because this entire thing was born from just an unimaginable loss.
It really was.
I want you to just, for a second, mentally transport yourself. You're on the tarmac in Ahmedabad, India. It's a warm evening, June 2025. You're on Air India Flight 171, a big wide-body jet, getting ready for a routine flight to London.
You hear the usual sounds, right? The final cabin door clangs shut. The safety briefing is just kind of background noise.
Exactly, and then you feel it.
Yeah.
That familiar, powerful surge as the engines spool up.
That feeling of immense power as the plane rotates, it lifts off the runway. For the 242 people on board, passengers and crew, it's just pure routine. But the timeline here, according to the investigation, is just frighteningly tight.
30 seconds, that's it. 30 seconds from the moment the wheels left the ground until everything went catastrophically wrong.
Everything.
The analysis found that the engines lost power almost instantly. Not a slow fade, not a degradation, but a sudden, simultaneous failure.
And the reason was, it's just bizarre. The fuel control switches for both these massive engines had been cut off.
Imagine what that sounded like. I mean, the deafening roar of takeoff just vanishes. It's replaced by this terrible, unnatural silence.
It's broken only by the shriek of the wind rushing past the airframe. And inside the cockpit, the recordings, they capture this frantic, immediate shock from the pilots. They're not running through checklists.
No.
They're questioning each other in just total disbelief. Did you just cut power? What systems failed? They had seconds, not minutes, to figure out an impossible failure.
And the altitude they had, it just wasn't enough for any kind of meaningful recovery. They were way below that critical 3,000-foot threshold.
No options. They couldn't glide to a runway, couldn't even turn back.
They were basically managing a controlled descent into an inevitable impact. They were passengers in their own aircraft's final moments.
And that, right there, that is the definition of the nightmare scenario. It's the moment the ability to prevent the crash just expires.
When the aircraft finally hit the ground, it was the deadliest aviation disaster in a decade.
Yeah.
And here's the number. This is the number that haunts the engineers who later developed Project Rebirth. Out of 242 people on that flight, there's only one survivor.
One person.
One person to tell the story. That stark, horrific statistic, 241 fatalities to one survivor, that was the emotional, the ethical catalyst for this entire innovation.
The scale of that loss, it just demanded a response that went beyond, just tweaking the existing systems. Aviation safety, it traditionally focuses on what we call active safety.
Right, all the stuff to prevent the crash in the first place. System redundancy, pilot training, all of that.
Exactly. But this catastrophe, it forced a radical leap into what's called passive safety.
Meaning, if you can't stop the crash from happening,
You have to design the system to make the crash survivable.
that's the moment. That's where they had to shift their focus from preventing the accident to just mitigating that final fatal impact. They were looking for a second chance mechanism for those last few seconds.
So to really get how audacious Project Rebirth is, we have to first define the problem they're trying to solve. And it's really just the sheer physics of impacts. The villain here is sudden, rapid onset G-forces.
Okay, so before we get to the external airbags, what does modern aviation already do? What is passive safety now?
It's a really detailed system, but it's all internal. So current passive safety has, let's say, three main parts. First is structural integrity, basically creating a safety cell like a roll cage.
Kind of like a Formula One car.
Yeah.
The outside just crumples, but the driver's pod, the cell, stays rigid.
Precisely. That survival space is absolutely paramount. Companies like Diamond Aircraft use composite structures to make sure the cabin space stays intact, resists crushing.
Got it. What's number two?
Second is effective occupant restraint. That's your seat belts, your harnesses, keeping you in your seat. And third, and this is crucial, energy-absorbing elements built right into the seats and the floors.
So things designed to break in a specific way.
Exactly. They crush or deform in a very controlled manner when there's an impact, and that absorbs kinetic energy that would otherwise go straight into the human body.
And we have data on this stuff, right? I remember reading that NASA was all over this decades ago.
They were. Those tests basically set the baseline for all modern aircraft seats. A really key source here is a 1983 NASA report. It detailed research using modeling programs like, and this is a great name, the KRH program.
KRIH, I love it. No subtlety needed when you're modeling a plane hitting the ground.
Not at all. And KRH was what we call a finite element analysis tool. It modeled these dynamic crash scenarios, air-to-ground impact, hard landings, overruns, and let researchers predict the exact forces the G-pulses felt throughout the plane.
And what did KRH find? What are the forces like inside a survivable crash?
Well, looking at tests like the controlled crash of an L-1649 aircraft, they found that even in survivable conditions, the jolts are significant. Specifically, the longitudinal pulses through the floor hit a static equivalent of less than 9G.
Okay, let's pause there. The difference between a static load and a step pulse, because that sounds like where things get really lethal.
Absolutely. A static load, let's say 9G, is the force your body can handle if it's applied slowly and evenly. But a step pulse is a rapid, sharp spike. When the crash pulse is a 5G step pulse, that force arrives almost instantly.
In milliseconds.
Exactly. And the human body, especially the spine and the skull, has a very limited tolerance for that kind of rapid onset deceleration. That sudden jolt is what causes the internal injuries. Shear forces on the brain, catastrophic spinal compression, even if the total G load seems manageable.
So it's not just the force, it's the speed of the force. The rate of onset is the real villain.
It's the villain.
Yeah.
And this is actually why the size of the aircraft surprisingly works in your favor.
Wait, how? How does a massive plane hitting the ground slow down less suddenly than a small one?
It's the sheer volume of crushable structure. Think of the fuselage not as a rigid tube, but as this series of connected frames and bulkheads. In a wide-body plane, there's just so much more structure, metal, systems, galleys, cargo between the point of impact and you sitting in the cabin.
I get it. So the size itself provides this huge unintentional crumple zone. The crash energy has to tear through and deform all that stuff first.
And in doing so, it spreads the deceleration pulse out over a longer time, maybe 150 milliseconds instead of 50.
And that extra 100 milliseconds is literally life or death.
It is. It dampens the peak G-force that gets to the passengers and makes it more of a very firm but survivable push. It's why crashes in big airliners often have higher survival rates than similar impacts in smaller planes.
That's a fantastic distinction. Okay, now let's compare that to cars. We know deployable systems work in cars.
We do. Modern car safety is basically defined by deployable shock absorption. Look at side airbags. Real-world crash data proves they work. They've drastically reduced the average injury severity score from 33, which is a severe injury, down to 21.
That's a massive, measurable win for passive safety, but it's internal, and it's dealing with a much lower amount of energy.
Precisely. So the core question Project Rebirth is asking is this. If internal systems can mitigate G-forces in a car, can we scale that solution up exponentially to save an aircraft when its own crumple zone isn't enough, especially in that sub-3,000-foot total power loss scenario?
Yeah, that absolute worst-case scenario where the G-forces just exceed what the human body and even the plane structure can handle. They need something that can actively change the physics of the crash in the last 2 seconds.
And the complexity of solving that. It's why this feels like a technological Hail Mary.
We have to give credit to the architects here, Eshel Wasim and Darsan Srinivasan, students from the Birla Institute of Technology and Science in Dubai. They didn't just propose airbags, they came up with this whole dynamic, coordinated, three-part rescue strategy.
And it has to start with a brain.
The brain, phase one, the AI crash detection.
Right, because a human just can't do it. You
Yeah.
can't process the data, calculate the trajectory, confirm the situation is unrecoverable, and then trigger everything in time. We're talking less than 5 seconds before impact.
So what is this AI watchdog looking at exactly?
It's a parallel safety framework. It's not flying the plane. It's just watching. It's supervising the high-level stuff, altitude, velocity, but it's also digging into complex sensor data on engine integrity, weird flight path deviations, even pilot inputs. It's looking for the statistical signature of a complete, unrecoverable failure.
So it's not just one thing, it's synthesizing dozens of data streams looking for that perfect storm. How specific does that have to be? Give me an analogy.
Okay, let's use the daily life analogy engine. Think of this AI as the ultimate smoke detector and carbon monoxide alarm for the sky.
Okay, I like that.
It's not trying to fly the plane, it's just quietly sitting in the background, monitoring the conditions, and it's looking for that very specific set of readings like rapid deceleration plus low altitude plus zero engine output that just screams, immediate danger is unavoidable.
It's waiting for the one signal that means it has to take over. Right now.
Instantaneously. And the sources are clear that this isn't purely autonomous. There's a really crucial human-centered AI, or HCAI, nuance here.
The human in the loop.
Exactly. The system is designed to activate automatically once those criteria are met, especially below 3,000 feet. But, and this is a big but, the captain can override the deployment.
So they have a few seconds, a few heartbeats to hit a big red no button.
A veto.
Yeah.
Just in case they're doing some highly unusual but still controlled maneuver that the AI might misinterpret.
So where does that put this on the automation scale if, level 1 is fully manual and level 10 is Skynet?
It puts it pretty squarely at level 6. That's where the computer executes the action automatically, but the human retains veto power for a very restricted amount of time. The system lets the human intervene before the action is locked in.
That level of trust, it requires near-perfect reliability because if the pilot overrides it 2 seconds before impact, they have to be absolutely certain the AI is wrong.
They do. The engineers have to bank on the AI being right 99.999% of the time in that window. Because once that AI locks in its decision, phase 2 begins. The muscles engage, and the plane is fundamentally transformed.
Right. Phase 2, turning the plane into a giant aerodynamic nightmare. Or, as we said, a protective marshmallow.
It's the external smart airbag system, and the challenge here is just scale and speed. These huge airbags have to deploy from storage in the nose, the belly, the tail, and form a complete cocoon around the fuselage in under 2 seconds.
2 seconds. From a sleek aluminum tube to this massive bulbous deceleration device, what kind of materials can even handle that?
They're banking on next-gen material science. The design specifies these high-performance layered fabrics. We're talking about combinations of incredibly strong fibers like Kevlar.
Okay, the bulletproof vest material.
Right. Then TPU, which is thermoplastic polyurethane for weather and abrasion resistance. And then there's Xylon.
Xylon. That sounds like something from a sci-fi movie.
It practically is. It's this liquid crystal polymer fiber that is one of the strongest man-made organic materials we have. It has incredible heat and impact resistance.
So this isn't the stuff in your car's airbag. This is body armor, but for a 200-ton aircraft.
Precisely. The core idea is to create a shell that distributes the impact force across the widest possible area. So let's use the analogy engine again, but this time for sports.
Okay.
Imagine trying to catch a massive bowling ball falling off a roof. If you try to catch it with your bare hands, the force breaks your fingers.
Right.
But if you catch it with a giant Kevlar reinforced trampoline, the force gets absorbed and distributed. This system is trying to turn the plane into that giant, shock-absorbing, Michelin man-like cocoon seconds before it hits the ground.
The cushioning is key, but as we said, G-forces are all about the speed of deceleration. You need more than just air to slow that jolt down.
And that brings us to phase 3, the secret sauce. This is where the system tries to actively slow the plane down and add another high-tech layer of absorption.
Okay, so how do you actively slow down a crashing plane?
2 ways. First, if the engines are still working, even partially, the AI automatically engages reverse thrust. The designers figure this could cut the speed by up to 20% just before impact.
That is a huge reduction. But it's also terrifying. We talked about the C-17 military plane doing this.
Right. Military transports like the C-17 are built tough enough to divert their main thrust forward while they're still in the air. They do it for tactical reasons, to make these incredibly steep descents like 15,000 feet a minute.
But for a commercial airliner, that's normally an absolute no-go structurally.
Totally forbidden. But in a crisis where the alternative is certain death, A 20% speed reduction is a game changer.
And what if the engines are dead, like in the Air India scenario?
Then you go to the backup systems. Specialized gas boosters, they're sort of like cold gas thrusters that NASA has studied. Things like fluidic emergency thrusters. They provide these precise, non-explosive bursts of cold, inert gas.
And what's the goal of that? Not to slow it down, but to stabilize it.
Exactly, to make sure the plane hits the ground flat on its belly
Yeah.
on that big airbag cushion instead of pitching over into a catastrophic nosedive. You want the maximum surface area for impact.
Okay. And then comes the really innovative part you mentioned, the impact fluids.
Yes. The shear thickening fluids, or STFs. This is the really clever part.
Okay, so break this down for me. What is a shear thickening fluid beyond the classic cornstarch and water experiment?
It's basically a liquid that's packed with a super high concentration of nanoparticles. Under normal conditions, it just behaves like a regular low viscosity fluid. The particles can slide past each other easily.
But if you hit it hard, like with a punch or a plane crash,
The physics just completely changes. That sudden high-energy input forces the liquid to behave like a solid. It's a mechanism called particle jamming. The nanoparticles momentarily pack together so densely they can't flow anymore, and the fluid's viscosity just skyrockets. It effectively hardens on impact.
wow. So it turns kinetic energy into viscous resistance almost instantly.
It does. It's already used in things like high-end body armor because it gives you incredible impact resistance without the weight and rigidity of solid armor plates. So Project Rebirth proposed putting this STF technology inside the layers of Kevlar and Xylon.
Creating a flexible armor shell that instantly becomes a rigid energy absorber at the moment of impact.
That's the idea. And you can't forget the final passive features too. A bright orange shell for visibility, integrated GPS, infrared beacons, illuminated exit paths. It's designed not just for survival, but for rapid rescue.
So the engineers, Wasim and Srinivasan, they built small-scale prototypes with CO2 canisters and ran these extensive computer simulations. And the claim from those tests was it was monumental. The simulations showed a reduced impact by more than 60%.
A 60% reduction. I mean, that is the difference between mass fatality and a highly survivable event. But this is the critical turning point in our deep dive.
This is where it hits the real world.
Yes. When this proposal got out into the wider engineering and aviation communities, the skepticism was immediate, fierce, and overwhelming.
It seems like the technical community, on forums like Reddit, they saw the flaws the simulations might have missed, the real-world flight dynamics. And the number one criticism was aerodynamics.
This is the big one. It's a killer. An aircraft's entire job is to maintain its lift-to-drag ratio and stay stable. When you suddenly inflate massive external airbags, which are basically giant non-aerodynamic balloons, you create this instantaneous massive increase in drag.
You completely destroy the designed airflow over the wings and the tail.
You turn a sleek hydrodynamic shape into a blunt instrument. And the immediate result of that, especially in the very scenario this is designed for when engine power is already lost, is a stall.
A stall, the wings lose lift, and the plane just plummets.
It plummets, and often with extreme attitude changes. A rapid pitch down, an uncontrollable spin. And if a plane stalls and drops like a rock, hitting the ground nose down, no external airbag in the world can save the occupants from those vertical G-forces.
One engineer mentioned the shift in the center of pressure versus the center of gravity. Can you break that down?
Yeah, that's a critical point. So the center of gravity, the cog, is the plane's physical balance point. The center of pressure, or COP, is the average point where all the aerodynamic forces are acting. For stable flight, the COP needs to stay slightly behind the cog.
Okay.
But if you deploy a massive draggy balloon on the nose of the plane, you instantly shift that center of pressure way forward.
That sounds bad, like trying to balance a pencil by putting a giant weight on the eraser end.
That's a perfect analogy. That forward shift in the COP creates this huge, unwanted pitching moment. The nose would be forced violently down. The sheer force of the air hitting those newly inflated bags at 200 knots would either tear the plane apart or guarantee a lethal impact attitude before the bags ever even touched the ground.
So beyond the immediate aerodynamic fatality, there were also huge practicality issues, starting with the biggest problem in aviation, weight.
The weight penalty is a massive barrier economically. You're adding the mass of all that Kevlar and Xylon fabric, the gas boosters, the pressurized tanks, or solid rocket motors for inflation, the impact fluids.
And how does that translate for an airline's bottom line?
It's dramatic. The weight is directly tied to fuel burn and payload. Some sources estimate that even a 5% increase in the plane's structural mass could cut the revenue-generating payload passengers and cargo by as much as 20%.
20% less payload. That's hundreds of thousands of dollars in lost revenue on every single flight. It makes the system completely unaffordable before you even talk about the complexity.
It's a non-starter in the commercial aviation industry. It would kill profitability and range, making the plane economically unviable.
And then there's the terrifying idea of an accidental deployment. If this thing is designed to go off automatically in 2 seconds, what if it's wrong?
The chance of it deploying by mistake, from a sensor glitch or a lightning strike, has to be zero. And in aviation, near zero is not good enough.
Right. Aviation safety is built around interlocks to prevent catastrophic mistakes, like the system that stops the thrust reversers from engaging in mid-air unless it senses weight on the wheels.
Exactly. And Project Rebirth is designed to bypass all those interlocks in the name of speed. It relies on squibs, small explosive charges, and sensors that have to tell the difference between severe turbulence, a massive bird strike, and a true unrecoverable crash. A faulty sensor could doom the aircraft.
The final, really grim concern was about what happens after the crash. The critics called it the horrendous cocoon.
Yeah, the secondary hazards. So the bag absorbs the impact, but what if there's a fire from a ruptured fuel line, which is common? The Kevlar, the Xylon, the STF material. It could melt, it could fuse, it could just form this massive, rigid, hardened shell around the plane.
Trapping the survivors inside.
Exactly. If the bag material blocks or seals the emergency exits, or if the sheer bulk of it prevents rescue workers from cutting into the fuselage, the very thing designed to save them becomes a fatal trap.
Someone called it a plastic Pompeii, which is a terrifying image.
It is. So you solve the G-force problem, but you introduce 3 new, potentially fatal problems: aerodynamic stall, crippling weight, and post-crash entrapment.
That's why the reception was so brutal. And it all comes down to the trust hurdle.
It does. Any system operating at that level 6 of automation, where human intervention is so limited, has to meet an impossibly high standard of reliability, safety, and trustworthiness. Aviation demands predictability, and Project Rebirth introduces radical uncertainty into the most critical phase of flight.
So we've pretty much established that the full Michelin Man plane is, well, it's likely never going to fly. The physics and the economics are just too real.
That's the pragmatic conclusion, yeah. But the true value of Project Rebirth isn't the whole system. It's the intense component-level innovation it forced. It's an innovation inheritance that we can use without the fatal flaws.
Let's talk about the spinoffs. What parts of this radical idea can actually make flying safer?
Okay, first, the AI pre-crash analysis framework itself. The AI needed to predict an unrecoverable descent below 3,000 feet. That's incredibly valuable on its own.
And it doesn't need to trigger an airbag. It could just be a better warning system in the cockpit.
Absolutely. It could give pilots those precious extra seconds to brace for impact or attempt a final stabilization maneuver. That kind of AI could even revolutionize maintenance by spotting tiny statistical anomalies in engine performance long before a failure.
The second area, and this one is really exciting to me, is the advanced materials. The pairing of those fabrics with the shear thickening fluids.
This is where the tech is most transferable. We know STFs harden on impact. So why waste that on a risky external bubble?
Where can we use it inside the plane?
It could completely revolutionize internal passive safety. Imagine incorporating STFs into the material of seat cushions, seat backs, the cabin floor, even the overhead bins.
So on impact, your seat instantly stiffens, distributing the G-load across your whole body and absorbing the energy.
Exactly. NASA spent decades designing energy-absorbing seats. STFs are the next exponential leap in that work. They offer huge weight savings compared to normal, crushable materials while providing superior protection. It solves the weight problem and the G-force problem at the same time, but safely inside the cabin.
That just makes perfect sense. You get all the benefit without any of the aerodynamic risk.
Third is the cold gas stabilization idea. Using those controllable cold gas boosters, it could be a highly controlled last-ditch stabilization tool.
Not for deploying airbags, but for controlling the plane's attitude during a hard landing or an emergency on, say, an unprepared surface.
Precisely. In a low-speed crash, like an overrun off a runway, just controlling the pitch and roll in the final moments could prevent a wingtip from digging in and causing a fatal rollover.
So the whole project, even as this unrealizable concept, it forces us to re-examine automation in a crisis.
It really reinforces the goals of human-centered AI. Project Rebirth tried to solve the no human control problem with a purely automated solution. But the reaction proves that for these high-stakes systems, Real progress is about achieving both high automation and high human control. The pilot has to be able to trust, verify, and override the machine.
So the paradox is that the solutions they came up with to remove human control are now showing us ways to aid human control with better data and better internal protection.
That's the legacy. And it brings us to a final, really provocative thought about the future of aircraft design.
Okay, let's connect all the dots. We know from that 1983 Aerospace program that big planes are already safer because they have more crushable structure.
Right. Structure equals time, and time equals survival.
So if that passive protection works, should the future of crash safety move away from complex external systems entirely and instead just focus on designing fuselages with intentional, massive, dedicated crush zones?
That's the pragmatic lesson that Project Rebirth's failure teaches us. Instead of adding a reactive system on the outside, put the engineering effort into designing the plane's primary structure to be sacrificial. Create a dedicated engineered crush cell that's designed to deform and absorb energy, all while protecting a hardened internal safety cell for the occupants.
It's more reliable, it's predictable, and it respects the aerodynamics of the aircraft.
It's the lesson learned from tragedy.
This has been an incredibly detailed and, I gotta say, a difficult deep dive into the engineering and ethics around Project Rebirth. We started with the unimaginable tragedy of that Air India crash.
We dissected the three-part rescue strategy, the AI brain, the external Kevlar airbags, and the stabilization with reverse thrust and those shear thickening fluids.
But the core of it was that reality check. The massive skepticism about the aerodynamics, the crippling weight penalties, and the unacceptable risks of accidental deployment and post-crash trapping.
Ultimately, the project's real legacy is in its components. That AI framework, the application of STFs for internal safety, the cold gas stabilization, all things we're very likely to see integrated into commercial flight in the coming decades.
Well, thank you for sharing your sources on this. It's controversial, but it's an essential deep dive into where innovation meets the harsh reality of physics.
My pleasure. We hope this gave you a full view of not just the dream of Project Rebirth, but the complex, pragmatic steps that actually move aviation safety forward.
Until next time.